good morning. Welcome you all to this NPTEL course on electrical distribution system analysis. Today, we'll be focusing on practical insights into electrical distribution system, and we'll take you around the distribution system of the academic campus of IIT Roorkee for better understanding about the subject. Today, we will take you on a tour to show how the electric power flow from the substation to individual rooms, focusing on key components like transformers, diesel generators, feeders, solar PV generation and loads. We will demonstrate how each part contributes to delivering power efficiently. Let us join us as we explore how these components work together to maintain seamless power distribution across the institution. We begin our tour at the 33/11 kV substation and the 11 kV DG station. This will serve as the starting point for our comprehensive analysis and implementation plan. Let's start by discussing the single line diagram of IIT Roorkee power distribution system. The campus features two 33/11 kV transformers and 4 diesel generators, with 2 of the diesel generator represented as a single unit in the diagram. Additionally, there are 10 outgoing feeders and 24 11 kV substations distributed throughout the IIT Roorkee campus. This setup ensures a reliable and efficient power supply to all parts of the campus. First and foremost, it is crucial to wear protective gear such as helmets and safety vests before inspecting any substation. The power supply to IIT Roorkee comes from the 220 kV Ramnagar substation through two ways, an overhead line and an underground cable. Initially, the campus relied on a 33 kV overhead line, which was prone to frequent tripping and disturbances, especially during the rainy season. To ensure a reliable power supply without seasonal disturbances, we laid a dedicated 33 kV 3C cross 300 square mm 5.4 km underground cable from the 220 kV Ramnagar substation to the 33 kV IIT Roorkee substation. Moving on, this is the isolator from the 33 kV line. An isolator is an essential device used to ensure that an electrical circuit is completely de-energized for maintenance or service. It provides a visible break in the circuit, enhancing safety for maintenance personnel. This particular isolator is equipped with insulators to support and separate the electrical conductors, ensuring there is no unwanted flow of electricity while the circuit is being worked on. Following the isolator, you will see the bus bar, which act as a conductor, collecting electrical power from the incoming feeders and distributing it to outgoing feeders. The power is then fed to two transformers. Before reaching the transformers, the power passes through another isolator, an SF6 circuit breaker and a current transformer. These are the two 33/11 kV transformers with a firewall between them for safety purposes. This firewall ensures that if there is a problem or fire in one of the transformer, it does not affect the other one, allowing one transformer to provide supply to the campus independently. This transformer has an on-load tap changer, so called OLTC, with 16 steps and uses an automatic voltage regulator AVR to automatically adjust for voltage deviations, ensuring stable operations. It's rated at 10 MVA with 33 kV high voltage and 11 kV low voltage, featuring ON-AN cooling, a Diane 11 vector group and an impedance voltage of 8.35%. It has no load loss of 6.5 kilowatt, a load loss of 55 kilowatt and weights close to 20420 kg. The nameplate shows different views, front, side and top, highlighting various valves and components, including filling set of filter, drain and sampling valves, as well as an air release plug and radiator valves. This setup includes panels for two transformers with two additional panels in the middle dedicated to the automatic voltage regulator. These panels enable control of the transformers from a central location, allowing for comprehensive monitoring of all transformer parameters. Any issues or faults within the transformers can be promptly identified and managed from within the substation, ensuring efficient and reliable operation. Now let us look into one of the 33 kV C&R panel. Here we can see different types of relays, trip alarms and energy meters, all integrated into this panel. Various switches are also present to manually control the operation of the transformers. Additionally, the panel includes indicator lights, selector switches and measuring devices to ensure the smooth operation and monitoring of the system. Zooming into the single light diagram, we observe three switches, one for the isolator, one for earth fault and one for the circuit breaker. As the transformer is currently in a healthy condition and operating normally, all switches are in the closed position. If there is any fault in the transformer, the relay will detect the issue and open the circuit breaker. If there is an earth fault or the isolator is open, then we can also see the switches for these are open. This device here is the trafo differential relay, a critical component designed to detect faults between the transformer winding by comparing the current on each side of the transformer. Its screen display various parameters and measurements such as current reading, and the right side shows different signals. When a trip or test occurs, the corresponding lights illuminate, offering immediate visual feedback. Alongside the differential relay, there is a multifunctional protection relay which integrates multiple protection functions into a single unit, ensuring comprehensive safeguarding of electrical systems. This relay also displays active signals indicated by glowing lights. Here is the annunciator, which acts as a visual alarm system for any faults. When a fault occurs, the corresponding signal will glow, altering the operator to the issue. This is the voltmeter indicating the voltage level. Additionally, we have the electronic bell for non-trip alarms, the hooter for trip alarms, and the electronic buzzer for DC fail alarms. Below this is the ammeter showing the continuous current flow, and the beneath it the frequency meter. This control panel features various indicator lights and buttons, each representing the status of specific functions or components within the electrical distribution system, such as circuit breakers, phases, and trip circuits. The color coding aids operators in quickly identifying the status of each component. This device here, a VAF meter, an electrical measurement device that combines the function of three distinct meters into one unit, measuring voltage, ampere and frequency. Next, we have the local remote selector switch and the SATEC PM180 high performance analyzer, a type of multifunction meter used to measure, analyze and display various electrical parameters essential for real time monitoring and energy management of the transformer. Lastly, we have various types of relays. The trip circuit supervision relay monitors the health and continuity of the trip circuit. The master trip relay ensures power disconnection between faults. The buckle strip alarm relay detects internal faults in oil field transformers. The OSR trip low oil level alarms detect sudden oil flow changes indicating serious faults. The WTI trip, that is WTI alarm, monitors transformer windings temperatures, while the OTI alarm monitors the oil temperature. These relays and control units collectively ensure the reliable operation and protection of the transformer. As you can see, these are the two panels for the automatic voltage regulators for our two transformers. The AVR system is designed to automatically adjust the transformer's tap changer, ensuring a constant output voltage despite fluctuation in input voltage or varying load condition. Now, from these transformers, power flows to different feeders within the IIT Roorkee distribution system. As discussed earlier, our system comprises a total of 10 feeders with each transformer connected to 5 feeders. These are the control panels for each feeder. From these panels, operators can directly manage and control all aspects of feeder operation, ensuring reliable and efficient power distribution throughout the campus. Each panel is equipped with essential control and indicators to facilitate real-time monitoring and management, thus maintaining the stability and efficiency of our electrical distribution system. This is the main incomer 1, which indicates that the power signal for the first transformer is routed to this panel. The mechanical operation switch here allows for manual switching between the test and service positions for the circuit breaker, ensuring safe testing and operational engagements. The level clearly indicates the position and directions for operations. Additionally, an emergency button is present for immediate action during any emergency situation. Moving on, these are all the feeders connected to transformer 1. The feeders are outgoing for new panel 1, outgoing to Bikas Nagar, to VIP and to Rajendra Bhavan. Here we also see the bus coupler, which is an essential component used to connect two bus bars. The bus coupler allows for flexible switching operations and improves system reliability by facilitating maintenance and fault isolation without interrupting the power supply. Generally, the bus coupler is kept in the open mode. Next, we see the feeders connected to transformer 2. These include the outgoing to WRL, outgoing to Bigyan Kunj, outgoing to the high voltage lab, and outgoing for new panel 2. Here is the incomer 2 similar to incomer 1, indicating the power signal for transformer 2 is present here. At the bottom of the panel, we find the local remote selector switch, which toggles control between local and remote operation. The ammeter selector switch allows the selection of different current measurements, while the breaker control switch, trip or close, enables manual tripping or closing of the circuit breaker. Above, this is the TCS relay or trip circuit supervision relay, which monitors the integrity of the trip circuit. The ammeter and voltmeter measures the current and voltage respectively in the feeder, with a voltmeter selector switch allowing for different current measurements. Additionally, the REF 615 protection relay is a multifunctional protection relay for feeder protection, and the Secure Elite 440 is a digital power meter for monitoring various electrical parameters. Indicators above these components provide quick visual feedback on the status and health of various system components and phases, aiding operators in effective system management. Zooming in on the Secure Elite 440 digital power meter, we see it is a crucial tool for energy management. It provides detailed and accurate measurements of electrical consumption, aiding in the efficient operation of electrical system. Here we observe energy consumption reading of 171942 watt hour for watt hours and 193557 VAH for volt ampere hours, indicating total and apparent energy consumed respectively. The ABB REF 615 is a protection relay used for feeder protection in distribution networks, offering comprehensive protection, control, measurement and supervision. It features status indicators for readiness, start and trip conditions, and a display showing real-time operational status and date and time. This relay includes multiple protection functions such as overcurrent, earth fault and thermal overload protection, supporting advanced control and monitoring capabilities to ensure the safety and reliability of electrical systems. Moving on, we have the lockout trip relay, which prevents re-energizing the system after a fault until manually reset. The TCS relay monitoring the integrity of the trip circuit, the PGIM annunciator providing visual and audible alarms for various fault conditions, a digital ammeter displaying current in the feeder, an emergency trip button for manual system tripping in emergencies, and various selector and control switches for local remote operations and manual circuit breakers tripping or closing. These are the actual 11 kV feeders in the field with all 10 feeders present here. The isolators present here ensures manual tripping in the field if a trip signal from the panel does not work, and they are also used for maintenance purposes. This is the ABB RTU 560 panel, a remote terminal unit essential for data acquisition and control in both electrical and industrial automation system. The RTU 560 modules collect and transmit data from various sensors and devices to a central control system, that is the SCADA system. LED indicators provide visual status updates for power, communication and module health, while communication port connect the RTU to other devices and networks, facilitating data transmission and remote control. The RTU 560 panel is crucial for monitoring and controlling remote equipments, ensuring reliable operation and real-time data acquisition in electrical systems. Here we also have a float cum boost charger panel used to maintain battery charge in electrical networks. Key components of this panel include top row indicators, a DC voltmeter and DC ammeter, a hooter, selector switches, push buttons and circuit breakers. The top row indicators provides a quick visual status of the system operation, ensuring that any fault or operational modules are easily identified. The DC voltmeter and ammeter display the current voltage and current, aiding in the monitoring of the charging process. The selector switches and push buttons offer control over the charging modes and alarm handling, while the circuit breakers protect the system by isolating individual loads as needed. This setup ensures that batteries are charged optimally, providing reliable power for our electrical systems. These are the 4 diesel generators present here, which serve as crucial backup power sources for our electrical system. Diesel generators are known for their reliability and efficiency in providing power during outages, ensuring continuous operation of essential services. Each generator is designed to automatically start during a power failure, maintaining a steady power supply. This is the chimney for the diesel generator. It is designed to safety vent exhaust gases produced during the operation of the generators, ensuring a safe and clean environment. All the diesel generators have the same rating. They are rated at 1500 kVA and operate at 11 kV, providing substantial power to support the facility's need. These generators are integral to our emergency power system, offering a robust solution for maintaining electrical stability during unforeseen power disruptions. Adjacent to the generators, we have a diesel storage facility with a capacity of 20 kiloliters. This facility is designated for restricted entry due to the highly flammable nature of the material. It includes a large covered diesel storage tank, associated piping and a control panel for monitoring and managing the storage system. Here we see the tankers for the 4 diesel generators sets labeled at DG 1, 2, 3, 4. These tankers are supplied with diesel from the 20 kiloliter underground diesel storage facility. Each tanker stores fuel specifically for its corresponding DG set, ensuring a consistent and reliable supply of diesel for power generators. This is the diesel level indicator on the tankers for the DG set, displaying the current diesel level within the tank, marked with measurement from 100 to 990. These indicators help monitor the fuel level, ensuring that each DG set has an adequate supply of diesel operations. These are the four control panels for the diesel generators. These panels are used to monitor and control the operation of the DG set, ensuring they function correctly and efficiently. Each panel features indicators, lights and meters that provides real-time status and operational matrices such as voltage, current and frequency. Control buttons and switches enable operators to start, stop and reset the generators, while digital displays offer detailed performances, informations and alert operators to any alarm or faults. Key features of the control panel includes engine control relay that controls and monitors the DG set, displaying operational status and setting. Multifunction protection relay DEIF GCU 100 protects the generator by monitoring various parameters and tripping in case of faults. Alarm annunciator provides visual and audible alerts for various faults and operational conditions. The single line diagram on the control panel indicates an open state as shown by the disconnected lines here. This means the DG is not in operation currently. Zooming into the engine control relay for a diesel generator manufactured by Deep Sea Electronics, the relay screen indicates the current status of the generator, showing generator at reset or generator at rest and stop mode, which means the generator is currently not in operation. The control panel includes buttons for starting, stopping and resetting the generator, as well as navigating through various settings and operational modes. This relay is crucial for the efficient and safe management of the generator, allowing operators to monitor and control its function accurately. Here is the alarm annunciator panel for the diesel generators. This device is designed to alert operators to various fault conditions, helping ensure the safety and reliability of the generator system. Each window on the panel corresponds to a different potential alarm condition such as overfrequency, undervoltage or short circuit. Currently, the low oil pressure alarm is active, indicating a potential issue that needs attention. The panel also includes buttons for testing, accepting and resetting alarms. This is a multifunction protection relay GCU 100 by DEIF designed to provide comprehensive protection for diesel generators. This relay monitors various electrical parameters and conditions, ensuring the generator operates within safe limits. It features start stop buttons, status indicators and navigational buttons for setting and data display, helping to maintain the reliability and safety of the generator system. These are a set of 4 NIS, that is neutral isolator switch panel. Each panel is equipped with control buttons, indicator lights and selector switches to manage the operation of the respective DG sets. These panels are essential for ensuring safe and effective switching and isolation in power distribution system, contributing to the overall reliability and maintenance of the generator setup. Let us see the future of the 4 DG set. Each DG set has a substantial capacity of 1500 kVA, powered by robust 12-cylinder V-shaped air-cooled engines manufactured by Perkins, delivering 1785 bhp at 1500 rpm. The alternators are self-excited and self-regulated, featuring brushless excitation from Toyo Denki. These DG sets draw power from fuel tanks with a capacity of 990 liters, consuming approximately 250 liters per hour at full load. These features ensure reliable and efficient performance essential for our operations. Here you can pause and see how the 4 diesel generators are integrated into the power system of IIT Roorkee. Let us proceed to the biotech substation, which serves as an actual 11 kV feeder for the biotech facility. Transitioning to the 11/415 kV biotech substation, we observe a critical component of the power distribution system. The 11 kV substation panel setup, the single line diagram SLD provides a clear illustration of power flow beginning from the leftmost section where it enters from the 33 kV substation, marking the high voltage supply feeding into this panel. Moving rightwards, the initial segment showcases the outgoing 11 kV line dedicated to supplying power to the workshop, ensuring a reliable energy source for this essential facility. Adjacent to this segment, three lines extend towards transformers, playing a vital role in stepping down voltage levels for subsequent distribution. Each of these three lines is outfitted with air circuit breaker, which are indispensable for fault current interruptions, thereby safeguarding the system's integrity and reliability. Above these breakers, we find multifunction meters, especially LIT 440 models, which are instrumental in measuring various electrical parameters within the 11 kV substation. These meters display critical data such as current, voltage, and other electrical values, essential for monitoring and ensuring the power distribution system performance and stability. We can observe that the LL voltages in kV on these meters. By adjusting the settings, one can view the current flowing through the system, the power factor, the total power across the three phases in megawatts, and finally the system frequency. Zooming in on the leftmost side, where the power originates from the 33 kV substation, we see an ABB Safe Plus Ring main unit panel compliant with IEC 62271 200 standards. This panel includes an SF6 gas pressure gauge, crucial for maintaining appropriate insulation and arc quenching. Key specifications indicated on the plate below reveal a rated voltage of 12 kV, a rated current of 630 ampere, and a short circuit current rating of 21 kiloampere. Additionally, the panel is equipped with a short and earth fault indicator, essential for detecting and managing electrical faults, thereby enhancing the system's safety and reliability. Now, let us explore the feeder remote terminal unit, a critical component for monitoring substation equipment and real-time data acquisition from all incoming and outgoing feeders. The FRTU captures status signals of devices and performs automatic data logging, thereby enabling substation level control. In the top section, we find the communication modules and controllers which facilitate real-time data exchange with the central control system known as SCADA, thus enhancing the reliability and automation of the electrical network. Next, we examine the 800 kVA transformer. This substation houses three such transformers, each operating at a high voltage of 11 kV and a low voltage of 433 volt. The transformer has no load current of 41.99 ampere on the high voltage side and 1066.70 ampere on the low voltage side. It is a three-phase unit with a delta connection on the high voltage side and a star connection on the LV side. It features copper winding and an insulation class of F. The nameplate provides comprehensive information about the vector group, type of cooling, insulation level, and other specification, along with a lifting instruction diagram for safe handling. On the HT side of the transformer, we see the underground cable entering the transformer. A warning level at the bottom indicates the presence of high voltage 11 kV, emphasizing the need for caution when handling or operating the equipments. The vented cover aids in heat dissipation, ensuring proper ventilation for internal components. The HT side is marked with 1U, 1V and 1W, indicating the three phases. Similarly, the LT panel is marked with 2V, 2U and 2N. The overhead bus duct duct carries power from distribution to different loads. This electrical distribution system consists of a metal enclosure containing either copper or aluminum busbar for conducting a substantial amount of electricity. The bus duct is suspended from the ceiling and connected to the LT panel, facilitating the distribution of electrical power to various parts of the facility. Focusing on the bus duct, we observed how it carries power to incomer 3, which refers to the power coming from transformer number 3. Here we have an air circuit breaker present in the LT panel. This breaker is rated for 1600 ampere and can operate at a voltages up to 690 volt with a short circuit breaking capacity of 65 kiloampere, compliant with IEC 60947-2 standards. The control handles allow for connecting, disconnecting and testing the breaker, ensuring safe operation. Additionally, we have a multifunction meter, the WC 5000 model by L&T. This meter display real-time electrical parameters showing the line-to-line voltage as 405.9 volt. Various parameters such as line-to-neutral voltage, current, power measurements are also visible. For instance, the meter indicates a power consumption of 191 kilowatt, reactive power of 56.25 kVAr, apparent power of 199.1 kVA and a power factor of 0.959. Lastly, we observe the various 433 volt feeder where power flows from the 11/0.433 kV transformer. These feeders ensure the distribution of power to different parts of the facility, maintaining the overall efficiency and stability of the power distribution network. This is a panel for automatic power factor correction APFC, specifically rated at 415 volt with a capacity of 200 kVAr. The panel is designed to operate at a frequency of 50 Hz and is configured for a 3-phase system. It features 4 steps with step size of 2 into 25 kVAr, 1 into 50 kVAr and 1 into 100 kVAr to adjust the power factor automatically. The APFC panel includes a multifunction meter for real-time monitoring of voltage, current and power factor. It also has an auto off manual selector switch and an APFC relay to control the switching of capacitor banks. Each step is indicated by LED lights showing whether the respective capacitor bank is on or off. Now let us move to the next part, the rooftop solar PV. Here we can see various solar PV connected in series. All the solar PVs have different ratings. All the departmental buildings, office and hospitals and some hostels are equipped with solar PVs on this campus. Each panel has a capacity ranging from 250 to 400 watt. The total generation of the whole campus as of date is around 280 megawatt. Each building has a different peak generation capacity. We are now showcasing one of the solar rooftop PV system in detail for your better understanding. Here we can see the solar panel installation with electrical wiring and conduits. The cable are connected to the solar panels running through protective conduit to ensure safety and durability. This setup is typically for rooftop solar PV systems where the electrical connections are routed through conduits to protect against environmental damage and ensure reliable power transmission. Proper cable management and protection are crucial for the efficiency and longevity of solar power installations, ensuring that the system operates safely and effectively. All these cables coming from various solar panels are then connected to the solar PV inverter. The inverter primarily function is to convert the direct current electricity generated by the solar panel into alternating current electricity, which can be utilized by household appliances or fed into the grid. The cables are neatly organized and protected using conduits, ensuring safety and durability. Proper installation and maintenance of solar inverters are essential for the optimal performance of solar PV systems, facilitating effective conversion and management of the electricity generated by the solar panels. This is the specifications level of a delta electronic solar inverter. The DC input range is 200 to 1000 volt DC with an MPPT range from 460 to 800 volt DC. The AC output ranges from 220 to 380 volt AC and 230 to 400 volt AC for three-phase system at 50 to 60 hertz with a nominal power of 70 kilowatt and a maximum of 77 kilowatt. The inverter is now open, showing its wiring and internal components. The main AC connections are visible at the bottom with level terminals for L1, L2, L3, N as neutral and PE for protective earth. The cable carrying the line from the inverter to the terminal box is a 4-core 150 square millimeter copper 4C into 150 square meter CU cable. This cable is designed for high current capacity, providing efficient power transmission with minimal losses, ideal for connecting high power inverters to distribution systems. This is the communication module inside the solar inverters. The module includes terminals for various connections including VCC power supply, ground and RS-485 communication lines which facilitate data exchange between the inverter and external monitoring or control systems. Proper communication setup is essential for real-time monitoring diagnostics and effective or efficient management of the solar power systems. This is an AC distribution box ACDB rated at 160 ampere from Tata Power, where all the lines from the terminal box converge. This is the interior of the ACDB. The ACDB includes an electronic trivector meter from L&T for measuring electrical parameters like energy consumption. It also features circuit breakers, terminal box and a Siemens rotary switch for isolating and protecting various circuit. The large conductors are color coded for phases red, yellow and blue and connected securely to ensure safe and efficient power distribution. This shows a close-up of the electronic trivector meter. The model number is ER300P by L&T within the AC distribution box. The meter is used for measuring and recording various electrical parameters such as kilowatt hours and kilovolt ampere reactive hours. It is a bidirectional meter capable of measuring energy flow in both directions, which is essential for solar power systems that may both consume and feed electricity into the grid. The meter includes an RS-485 communication interface for remote monitoring and data acquisition, enhancing the management and efficiency of the power system. This is an auxiliary AC distribution box ACDB installed by IIT Roorkee, designed to serve as a backup for the primary ACDB. It contains a similar setup within an L&T electronic trivector meter, that is ER300P, for measuring and recording electrical parameters. The meter along with the circuit breaker and terminal blocks ensure that measurements can still be taken if the primary ACDB encounters any issues. This redundancy is crucial for continuous monitoring and billing accuracy, providing a reliable secondary source for power consumption data. Now, let us move to the ITAPS portal, a cloud-based management system for monitoring solar PV installation across various sites within the campus. This sophisticated system provides detailed information for each site, including site name, site ID, asset ID, AC and DC capacity, installation date and geographical coordinates. Let us specifically look into the IIT Roorkee Hospital PV generation. The dashboard reveals some compelling data. The lifetime energy generation by the hospital solar PV system stands at 212 megawatt hour, reflecting the total amount of energy produced since its installation. For the current day, the system has generated 121 kilowatt hour of energy. Additionally, we observe the performance ratio PR for the day at 66.7%, which measures the efficiency of the solar power system relative to its theoretical maximum output. The capacity utilization factor, that is CUF, for the day is 13.25%, indicating the actual energy generated compared to the maximum possible output over the same period. These matrices are crucial for assessing the performance and efficiency of the solar PV system, ensuring it meets the hospital energy needs effectively. Let us now examine the graph display the relationship between the AC power output of the solar PV plant and solar irradiance. The x-axis represents the time of the day starting from early morning to the late afternoon, while the left y-axis represents the AC power output and the right y-axis represent the irradiance. Key observations at this stage includes early morning 5:10 am to 7 am. Both the plant output and irradiance are at 0 or very low, indicating no or minimal sunlight. Morning, that is 7 am to 11 am, as the sun rises, the irradiance increases, leading to a corresponding increase in the plant's AC power output. This period shows a steady rise in both parameters. Now, moving to 11 am to 2 pm, the irradiance reaches its peak value and the plant AC power output also shows higher values. However, there are fluctuations indicating potential cloud cover, shading or other factors affecting the PV output. Afternoon time between 2 to 3 pm, it declines. Both irradiance and AC power output start to decline as the sun moves lower in the sky. Moving on to the graph for June 2, 2024, it illustrates the relationship between solar irradiance and the AC power output of the solar PV plant throughout the day. Starting from early morning at 5 am, both irradiance and power output gradually increase as the sun rises, with the irradiance curve and the power output showing a steady upward trend by mid-morning to midday. The irradiance reaches its peak, resulting in optimal solar energy conversion and maximum AC power output. The graph exhibits a smooth and consistent rise, indicating clear and sunny conditions. After midday, from 1 pm onwards, both irradiance and power output begins to decline as the sun descends. The decline continues steadily into the evening until both matrices drop to 0 by 8 pm as the sun sets. This graph effectively demonstrates a typical clear day with efficient energy conversion, with a minor dip around 1 pm, likely due to temporary cloud cover or shading, providing essential data for evaluating the performance of the solar power system. Using the ITAP portal, we can select different parameters to showcase in the graph from the menu. For instance, we can select different time frames for checking the output. Let us check the hourly AC power in watt. The graph shows that as irradiance increases, the AC power output also rises, peaking around midday before gradually decreasing as the day progresses, reflecting the typical daily solar energy production cycle. Now, let us check the lifetime energy in kilowatt hour. Each bar corresponds to the cumulative energy produced at regular interval throughout the day, maintaining a consistent energy output close to 200,000 kilowatt hour. The uniformity of the bar suggests stable and efficient energy generation by the solar system over the time. So, finally, let us examine the lifetime energy for the year 2024 displayed on a monthly basis. This visualization highlights the energy output for various months, providing a comprehensive view of the system performance over the year. We can also directly download this data for future analysis and research. Upon opening the Excel file, we see the month-wise energy output for this year, offering valuable insight into the seasonal variations and overall efficiency of the solar PV installation of IIT Roorkee campus. Now, let us observe this LT panel for the hostels, which plays a critical role in distributing electric power to various loads within the building. Each compartment is meticulously labeled for specific load designations or functions, indicating power feeds to and from different distribution points and equipments. This panel is equipped with switches and breakers for each load, providing necessary control and protection for the electrical circuits. Notably, some compartments are marked as spare, which are reserved for future expansions or additional loads. At the top, indicator lights provides a visual starts or visual status of the panel's operation, facilitating easy monitoring and maintenance. This LT panel is thus indispensable for efficient power management within the building. Next, we have the connection point where both grid and solar power system are integrated within the LT panel. Below, we can observe various load connections. Here, you can see the Schneider electric energy system or Schneider electric energy meter, a vital device used to monitor key electrical parameters within the power distribution system. The meter's display shows a line voltage of 415.1 volt, a current of 8.13 amps and a power factor of 0.984. These readings are crucial for assessing the electrical load, efficiency and stability of the power distribution system, which integrates both grid and solar power sources. Moving on, the section of the LT panel is labeled VTPN DB G.122, indicating it is a distribution board for a three-phase load. The panel includes a switch serving as a control and protection device for the connected electrical circuit. This configuration is essential for managing power distribution to various loads within the building, ensuring efficient and safe operation of the electrical system. The power from this panel is then connected to another distribution board of the same rating near the load point, from where the three phases will be distributed as single phases to various parts of the hostel. Here we can see the single phase power from the VTPN DB being received and further distributed. This board is equipped with 4 MCBs from Schneider Electric, which control and protect the electrical circuits. Each MCB connects to and supplies power to 4 individual rooms within the hostel. Finally, let us introduce you to one of the 2 battery energy storage systems, BESS, connected to the IIT Roorkee distribution system. This particular BESS is linked to the electrical department at IIT Roorkee. This is the centralized monitoring and analytic center at IIT Roorkee. This state-of-art facility is equipped with a supervisory control and data acquisition system designed for centralized monitoring and control of various electrical and mechanical systems across our campus. Here we find ourselves in the SCADA room, where large display screens provides real-time data, system status and analytics, enabling operators at their workstations to ensure the efficient and reliable operation of our infrastructure and to promptly address any emerging issues. Displayed on the SCADA dashboard is the single line diagram SLD of a 33 kV substation, providing a comprehensive overview of the system. This includes 2 incoming lines labeled as 33 kV incomer 1 and 33 kV incomer 2, each featuring isolators, earth fault switches and circuit breakers before the power enters the transformer. Additionally, the SLD illustrates the connection to 33/11 kV transformers, Trafo 1 and Trafo 2, which step down the voltage for further distribution. Moving to the status panel on the SCADA dashboard, we can observe the operational status and alarms for both transformers within the substation. Any active alarms or status changes will be highlighted here, ensuring that operators can quickly respond to any issues. Now, let us examine the SLD of the 11 kV substation. Here we see 2 transformers and 2 DG sets following the bus bar. We encounter the bus coupler under transformer 1. There are 5 feeders, with the first feeder branching into 2, making a total of 5 feeders under the first transformer. This configuration is mirrored in transformer 2 as well. Next, we move to the display of the HD network at IIT Roorkee, which provides a clear understanding of the network. All feeders are connected in a ring configuration, enhancing the reliability and continuity of power supply by creating a looped pathway that allows electricity to be routed in the event of a fault or during maintenance. This display also shows all 20 substations in the network. Here we have the SCADA overview for the 11/0.433 kilovolt biotech substation. We have discussed in detail. Now we are understanding through SCADA platform. Power from the 33 kV substation is shown flowing first to the Department of Mechanical and Industrial Engineering and then to 3 transformers. This dashboard display all voltage and current values along with active and reactive power flows within the substation. On the LT measurement dashboard, we can observe the electrical parameters from all incoming and outgoing feeders of the biotech substation. This includes voltage and current for all 3 phases, real, apparent and reactive power, as well as power factor, providing a comprehensive view of the substation's electrical performance. This SCADA system interface at IIT Roorkee provides a thorough overview of the institution's electrical distribution network, offering real-time monitoring and control of various substation components. The setup includes servers, GPS receivers, communication protocols and connections to different buildings. Finally, the CMAC Lab IITR highlights the configuration for monitoring and managing the electrical network, featuring central components such as an OWS monitor, a GPS receiver for time synchronization, and 2 SAS servers for redundancy and reliability. The communication protocol represented by green and red lines ensure robust data exchange between servers and components. The SCADA server panel, equipped with communication devices and networking equipments, forms the core of the SCADA system, facilitating seamless communication and data exchanges across the power distribution network. The high performance Dell EMC server and industrial PCs ensure that all information is consistently reflected across all systems. Finally, I would like to acknowledge the Electrical Engineering Department and Institute Works Department of IIT Roorkee, Tata Power, Delta Electronics, ABB, Hitachi and all other companies involved in executing such mega renewable integrated smart academic campus. This lecture would not have been possible without the dedication and expertise of our professors, engineers, staff and students. Thank you.